Okay, we have an interesting integral from the MIT Integration Bee 2006. This one's number 32. We have the integral from 0 to pi over 4 sine x plus cos x over 9 plus 16 sine 2x dx. Okay, this was a tricky one. Now, the first thing we notice here, it's just interesting that we've got different coefficients here in the numerator. This seems to make it kind of worse, actually. But the thing is, we do have a relationship between sine 2x and sine x plus cos x. We actually have two trig identities for this, one with sine x plus cos x. The other one I actually want to use is actually just using sine x minus cos x. I think this is going to work out a little bit better. And what I want to do is, in order to derive this, because I always forget the exact details, let's just square this thing. Now, just multiplying this out for the first term, we're going to end up with sine squared x plus cosine squared x. And then for the middle terms, we end up with minus 2 sine x cos x. And the reason it works out so nice is because this thing right here, this of course is just 1. And this right here, this is our sine 2x that we have in the denominator. So what I can do to simplify it, let's just write it as 1 minus sine 2x. And then what I can do is actually just solve for the sine 2x. And then just by rearranging, we'll solve for sine 2x. And we get sine 2x equals 1 minus sine x minus cosine x squared. So then let's just take this thing, we'll plug it back into our integral for sine 2x and continue. Okay, now that we've updated our denominator with this thing, I just want to distribute in this 16 and simplify this denominator. So let's just rewrite everything. Now for the first part, we multiply in 16, we just get a 16, we add that to 9, we're going to have 25 for the first term here, and then we distribute in 16, we're going to have 16 times sine x minus cosine x squared. And now at this point, I think we can see why I wanted to use sine x minus cosine x here instead of doing sine x plus cosine x. Because what I want to do here is just a u substitution. So what I'm going to do is I'm going to make my u equal to sine x minus cosine x. I'll take a derivative. So du, this is going to become cosine x. Derivative of cosine x is minus sine x. This becomes plus sine x dx. But this du value is exactly what we have in the numerator, just in a different order. So let's go ahead with this substitution. So first plugging in pi over 4 here. Sine at pi over 4 is 1 over square root of 2. Cosine at pi over 4 is also 1 over square root of 2. So our upper bound is just going to become 0. Plugging in 0, sine at 0, 0. Cosine 0 is 1. So the lower bound is going to become minus 1. Again, all this is going to be du. And then for our numerator, for 25, let's actually write this as 5 squared right now. And then for 16, let's write that as 4 squared, and this is going to become just u squared. Just for simplification, let's divide off this 4 squared. So I'm going to divide everything here by 4 squared. I don't want to change it, so let's do the same thing up front, and we'll have here 1 over 16. And then going ahead to simplify this, we have our 1 over 16 in front. Dividing 4 squared into 5 squared here, I can write this as 5 over 4 all squared. And then here the 4 squared is going to cancel. We're just going to have minus u squared, and then du in the numerator. And now from here, in order to finish this off, we actually could do partial fractions on this, the way this is in this form. But this is actually a really common integral, so I want to just use this formula down here. And for this, we have this in the same form here, a squared minus x squared, where our a value is just going to be this 5/4 value. So going ahead with this thing, we have our 1 over 16 in front. Then to our formula, we have 1 over 2, our a value being 5 over 4. Let's just leave it like this for now. And then we're going to have natural log absolute value a, which is going to be 5/4 plus x all over 5/4 minus x. Now from here, let's just get a little simplification on this part. If you multiply and divide all that stuff together out front, this is going to become 1 over 40 here. And then we just need to evaluate this first at 0. So when we do this, we're going to end up with ln of 5/4 over 5/4 plugging in 0. But that's just going to be 1, and natural log of 1 is 0. So this whole piece here is just going away. And then for the next part, we have minus. Natural log, plug minus 1 in, this is going to become 1/4 here in the numerator. And then in the denominator, 5/4 minus 1, this is actually going to become 9 over 4 here. Then just to clean this up, the 4's are going to cancel, and this is going to become 1 over 9. I can use that minus sign to just flip it and take the reciprocal. So what we have here is going to be 1 over 40, and then flipping this, we end up with natural log of 9. But for 9, let's just rewrite that as 3 squared, and that's just going to allow me to get the same solution MIT has, even though we could leave it right here, even though this is fine the way we have it. And then with log properties, we can take this 2 into the numerator here, and we have 2 over 40. But for 2 over 40, I can reduce that to 1 over 20. And for my final solution, we just get natural log of 3 over 20. Okay, there you have it. Really good one from MIT 2006. Thanks everyone for watching. Have a good day.